Hello everyone, this is Carter. I just want to preface this video by saying that I am not an expert on any of the things I'll be talking about in the video. I have just learned these in my own time, and I will be giving a summary on the content, and I believe this summary to be true, but I am very prone to making mistakes, so please kindly point out mistakes in my comment section if you find any. Okay, so I think I want to start, this is Linear Algebra 1, which is a first term undergraduate maths course, and we're starting off by talking about linear systems. So I guess the first thing we need to do is actually define a linear system, or what actually is a linear system. So we should probably do that. So here's a definition for you. Definition. Whenever I say a linear system, so by a linear system, or sometimes you might sort of say it as a linear system of equations. So by linear system or linear system of equations, we will mean sort of a set. We will mean a set of sort of m simultaneous equations Let me just see how this is working on my board. Yeah, actually I should probably zoom in on that, shouldn't I? Yeah. That's probably better. By linear system, we'll mean a set of m simultaneous equations in n real variables. In n real variables. x1, x2, all the way up to xn. These take the form, so that's what a linear system is. It's just a set of simultaneous equations. M simultaneous equations, where m is just a variable that represents how many we have, and n real variables, which is again a different variable to m, so they're different. They could be the same, but they don't have to be. So we have n real variables, and we'll just denote those as x1 all the way up to xn. And so what does this look like? Well, this looks like the following: a11 x1 add a12 x2 add all the way up to add a1n xn equals b1. This is that's sort of the first equation, right? So whenever you're dealing with a system, you'll typically have your a11, which is just a coefficient, so that's going to be like a real number. Well, we'll define it to be a real number. I guess it doesn't strictly have to be. And again, all these a things, they're all coefficients. And then the x is like your variables that you wanna find out what this is, if it is anything specific. Okay, and this b1 is what all of that stuff on the left hand side is equal to. So I guess one example of this could be something like 4x1 plus 3x2 equals 5. In this case, we only have two variables, x1 and x2, and my a11 is 4, a12 is 3, and my b1 is 5. Okay, but a linear system, as we said, can have sort of m simultaneous equations. So we need to sort of add in all of those m equations. Obviously, we don't actually know what m is, so we can't obviously add in manually every single one. But we can give a picture of what it would be like, and it wouldn't just be one equation, so I'm going to just do a couple more. So this would be our second equation, and then we can just sort of draw some dots here because we don't know what m really is. It could be anything. It could even be 2, in which case it will just be those two. But in general, we'll have m, so we'll just go up to am1 x1, add am2 x2, all the way up, add amn xn equals bm. Right, and this is the mth equation. Okay, so that's what a system, a linear system looks like. Okay, so you should be able to from now on know what I mean when I tell you, you know, linear system, right? It should be pretty self-explanatory from now on, because you have that definition. Okay, and I guess we also should say, let me just also extend this actually, because there is one thing I wanted to add, which I did say but I didn't write, which is we want ai, j, and bi to be real constants. So we say where ai, j, and bi are real constants. Okay. And I guess now that we have that, we need to talk a little bit more about what sort of a solution to that is, right? Because you should be familiar with simultaneous equations. So you might have seen before something like x plus 2y equals 7, and then maybe 2x plus 3y equals something else, right? Let's just say like 9. And you should probably know how to solve these coming into this course. And you would know that when you solve this, you might be able to find a value of x for which this is true, and for that value of x, a corresponding value of y, which makes this true. So they come in pairs, or tuples, or even you can think about them as vectors, and that's how we're going to think about them. So what we'll say is that any vector x1 all the way through to sort of xn, right? Because we have n real variables. So in the case where we just have x and y, or x1 and x2, for an x1, you can probably find a corresponding x2. That solves it. But when we have n real variables, then there'll be n different numbers that you get out of that if you have one solution, which is not guaranteed. So there may not be any vector which satisfies your system, but we'll get into that later. So any vector there which satisfies the above is a solution, right? Is a solution, or is said to be a solution. Yeah, it's said to be a solution. Any system, well, let's say any stem, okay. Any system with, I guess, greater than or equal to one solution is said to be consistent. So this is just some vocab for you. Is said to be consistent. And we also say that the general solution, so whenever we're solving a linear system, we typically want the general solution. So the general solution is sort of any description of all of the solutions of the system. Is any description, because just one solution by itself is often, sometimes it might be good enough, but you might also have infinitely many solutions, in which case you need to describe all of them, not just give one of them. So is any description of all the solutions of the system. Okay, and yeah, and basically, as I was saying, with these linear systems, as I was kind of saying, with these linear systems, you can have either 0, 1, or infinitely many solutions. And so those are actually the only three cases we can ever have, and we can prove this a bit later. Okay, so I now need to introduce you to the concept of sort of an augmented matrix. So an augmented matrix. So what is an augmented matrix? Well, an augmented matrix is kind of just like sort of an array or a list of numbers, but it's a special one because basically it's always of the form. So augmented matrix has the form sort of this A and then a line and then B. And we typically say that A is equal to the following, so it's just sort of like an array of coefficients. So it's going to be A11, A12, all the way up to A1n, and then A21, A22, all the way up to A2n, and then we have AM1, AM2, all the way up to AMN. So you can think about it sort of as an array of coefficients. That's pretty much what our augmented matrix is. And then we also have our B. So that's our B is just going to be those B1, B2, all of those things that we saw before. So everything on the right hand side of the equal sign. And this is actually a vector, which is kind of like a specific type of matrix. But that isn't, the details around that aren't too important. Basically, we're just going to bunch these two things up and put them into one matrix, or one sort of array of numbers. Okay. And so you really shouldn't consider these to be anything more than just arrays of numbers at this point in time. Don't worry too much about the specifics on that. Okay. So let's have a look at an example of such a system in three. So we're going to have three equations in three variables. So let me just try and move this down like so. Okay. Example. So an example of a system that we can have a look at is the following. So 3x plus y minus 2z equals minus 2. You might also see, x plus y plus z equals 2. And then you might also see 2x plus 4y plus z equals 0. This is a viable system. So this is an example of a system, right? Remember, this is our A1, this is our A11, which is 3, our A12 is 1, and our A13 is minus 2, and our B1 is also minus 2. And then we have our x, y, and z, which are our three variables, okay? So this should be pretty recognizable as a linear system, probably more recognizable than the definition I gave before, but we have to now find the general solution to the system. Well, one way we can do this is substitution. So substitution tells us to do the following. So we can number these equations. So that's 1, that's 2, that's 3, and we have from 3 we have that. From 2. From 2 we have that z is equal to 2 minus x minus y. So we're just solving that for z. And then what we want to do is we want to say substitute this into 1. So substituting this into 1 and 3. So we're going to substitute z equals 2 minus x minus y into equations 1 and 3. Substituting this into 1 and 3, we see the following thing emerge. So we get 3x plus y minus 2 times 2 minus x minus y, because that's our z. And that's going to be equal to, after doing some algebra, 3x So we're going to do plus y, but then we're going to have a plus 2y, so it's going to be plus 3y. But also our 3x from before will be plus 2x, so it'll be a 5x. And then we also have minus 4. So that there is going to be equal to, and the right hand side is still the same, is equal to minus 2. So that's our new equation number 1. And then substituting into equation 3, we will see that we have 2x plus 4y plus, 2 minus x minus y. This is a little bit easier to look at. So we have 2x minus x gives x. 4y minus y is plus 3y. And then we have 2. So that's going to be plus 2. And then that third equation we already can see is going to be equal to 0. So, well, what we now can see is that our z is nowhere to be found. So in these two equations here, let me just put a box around them. In these two equations here, you can see that our z is nowhere to be found. And what that means is that we've now reduced, via substitution, our system into a system of two equations in two variables, which is pretty standard, right? We can just do this kind of the same thing on this if we wanted to. So we can see now that we have those two equations. And now what we can do is we can do sort of 5. So we know that 5x plus 3y is equal to 2. We also know that x plus 3y is equal to minus 2. And we labeled those the new 1 and 3. So if we just do 1 minus 3, what you'll see is that we get 4x equals 4, which thus implies x equals 1. And then from here we backtrack. So if we have x equals 1, then we have 5 plus 3y equals 2, which is going to give us y is minus 1. And then we also can backtrack from our initial substitution that z is equal to 2 minus x minus y. So it's going to be 2 minus 1, which is 1, minus 1 is just going to be 2. So our final answer here is, so there is a unique solution. Thus, let's just see if this is on the, yeah, okay, it's still there. Thus, there is a unique solution. Just see how this recording is going. Just make sure it's working. Yeah, fine. Thus, there is a unique solution, and we can write it in a vector x, y, z like this, which we know is going to be equal to 1 minus 1, 2. Okay, and we can plug those back in and check. Right, but I guess there is a little bit of a problem with this. In that there is no problem with doing, let me just actually put this example in a box as well. There's no problem with using substitution here, right? Like, when I say there's a problem, I don't mean with like the way we just did it. I mean with trying to extend substitution. So one thing you might think after this is that, okay, so we have a method to solve a linear system like that I've just given you, but how can we generalize this to solve lots of linear systems? In fact, all linear systems. How can we solve all linear systems? Because what happens if I give you something like 1,969 equations and 2021 variables, right? It's almost not feasible. Definitely not feasible for a human to use substitution, but even to a computer, how do you program them to use substitution? Because in this case it was all nice, but there could be cases where it's not this nice, in which case the computer won't just be able to like solve for z in one of the equations and substitute it into the others, right? There can be much more complicated cases. There can be cases with zero solutions, infinitely many solutions. How can substitution identify those cases all the time? And I guess like it just leads to questions like that, which are slightly convoluted and difficult to answer. So I guess what I'm trying to get at is that substitution isn't really good enough, and so what we're going to be talking about for the remainder of the first chapter here is row reduction, which is why I introduced augmented matrices to you, because they are going to be used. So so what really So I'm going to sort of take you guys through row reduction. First of all, the first step of row reduction is always to transform your linear system into an augmented matrix. So notably, in the first case, so in the example above, we had the linear system 3x plus y minus 2z equals minus 2. That was our first equation. Our second equation was x plus y plus z equals 2. And our third equation was 2x plus 4y plus z equals 0. So that was equation number 3. And so the way we can transform this is by ignoring all the sort of variables. So we just ignore all our x's. So we ignore all of those. Sorry, I'm trying to draw a line through it. It's not quite doing what I want it to do. Yeah, so we just ignore all of those. So I'm just sort of crossing those out. Yeah, so we just cross out all of our variables. So all of the y's there, we cross them out as well. Then also all of the z's, we cross them out. So we just ignore all of those variables there, right? Hopefully you can see what I mean. And then we have some numbers, right? So I should probably write ones here. So 1y, 1y, 1z, 1z. And then we can write those coefficients in a matrix. So 3, 1, minus 2, 1, 1, 1, 2, 4, 1. But that's not it, because when we have an augmented matrix, we also have this line. And we also want to write these numbers on the right-hand side here. So the minus 2, 2, 0. So you can think about that line as pretty much the same as the equal sign. So augmented matrices are good because it means that we can sort of abstract the problem. We don't really care too much about the variables, about the names of the variables. We do care about the coefficients of those variables, but we don't really care about the names of them. For all I care, it could be 3 apples, 4 bananas, and 2 pears, right? It doesn't need to be x, y, and z, so we don't actually need that information. Which is why we can abstract the problem without completely ruining it by just transforming the system into an augmented matrix. And this also means that we can effectively at each step we can basically just take things very systematically. And the way that we're going to do that is by using what we call elementary row operations, or EROs, which effectively you can apply to the matrix and that don't affect these set of solutions as we apply them. So basically, you can apply some operations to this matrix, they'll change the matrix, and they'll bring us one step closer to the most general solution, or finding the most general solution, and they won't remove any information from the system as we apply them at each step. So they're quite useful, and so that's really and so augmented matrices are really quite good because they allow us to make this sort of systematic progress and eventually read off our solutions pretty much immediately. Okay, so I guess now I should really talk about EROs. So I'm probably going to write this perhaps somewhere up here actually. I don't know, because I kind of want to keep the row reduction sort of algorithm there. So I'm just going to go back up here and write about EROs. So we have EROs. So what are EROs? EROs are elementary row operations. Elementary row operations. Okay. So how do these work? Right, so I guess we should define them. So definition. An elementary row operation An elementary row operation, or ERO, is an operation of one of the following three kinds. One of the following three kinds. So just like sort of slightly zoom out a bit just to make this work. So the first sort of operation, so the first sort of kind of operation it could be is sort of swapping the ordering of any two equations in our linear system. So the ordering of two equations and I guess you can think about these also as rows. So rows in our augmented matrix, each row is just an equation, right? Because ultimately what we have is we have 3, 1, minus 2 representing 3x plus y minus 2, 2z is equal to minus 2, right? So each one of those rows is like an equation. And so basically what we can do is we can swap the ordering of those rows. So the ordering of two equations slash rows may be swapped. And the second sort of thing we can do is multiply an equation by a non-zero number, like scalar or number, real number. So an equation may be multiplied by a non-zero scalar. And the last thing that can happen is a multiple of one equation may be added to a different equation. And so those are sort of the three things that we can do. And I think they'll make sense more in context, but the ideas of them should be pretty simple, right? It's like multiplying both sides by the same number, right? That's allowed unless you're doing it by 0, in which case you just get 0 equals 0. So if I give you 4x equals 2, obviously x is equal to a half, but if I multiply both sides by 0, then I get 0 is equal to 0. So I've lost information, which is why we say it has to be non-zero. Also, I guess you could technically... if you have, and the third one is just saying if you have something like 4x plus 2y equals 5, and next you have 5x plus 3y equals like sort of 7, you could just add this to both sides, right? So you can add 4x plus 2y to both sides. So on this side you can go plus 4x plus 2y, and then you can do 7 plus 4x plus 2y, which is just 7 plus 5, right? Because 4x plus 2y is 5. So that just gives you 12. And so you can get a new system from those two, which says that 9x plus 5y is equal to 12. And that's all that third part is allowing us to do. It's allowing us to sort of combine these equations together. Okay, so let me just put this in a box. So that's EROs. Okay. So I guess we could also introduce some notation as to how we're going to sort of work with EROs in the remainder of sort of, I guess, our time dealing with linear systems. So we say let Sij denote the ERO that swaps rows I and j. And then B, we say that mi of lambda, so this denotes the ERO which multiplies row I, or equation, or really equation I, by lambda, which is not equal to 0. And then lastly we have let Aij of lambda denote the ERO which adds lambda times row I to row j. And we're going to say here that I cannot be equal to j for a few reasons. Because if it was, then we would have this ai lambda. So you're adding lambda times row I to row I. So you're going to be doing lambda I plus I, which is just the same as doing lambda plus 1 times I. So this is actually equivalent to mi lambda plus 1. So it's kind of redundant to have I equal to j because we already have dealt with that in our second ERO, which is mi of lambda. So that's some notation there. Let's put that in a box. And I pretty much, like with this notation, I should say it's not standard notation, but it will do us well. So with that, let's sort of go through an example of how we can use these EROs to sort of transform our augmented matrix. So that's the second part, right? So the second part of this step that we had before was to use. So here we go. So the second part is to use EROs to reduce augmented matrix. So how does this work? Well, I guess let's start off with our example. We had 3, 1, minus 2, minus 2, 2, 0, 1, 1, 1, 2, 4, 1. So I guess some stuff that we can do to this is we could swap the first two rows. So that's going to be S1, 2. And so what that's going to do is it's going to give us 1, 1, 1, 3, 1, minus 2, 2, 4, 1, 2, minus 2, 0. Now what we can do is we can do this, A1, 2, minus 3. So you're doing minus 3 times row 1 plus row 2, right? And when you do this, you're going to see you're going to have minus 3 plus 3, which is 0, minus 3 plus 1, which is minus 2, and minus 3 plus minus 2, which is minus 5, and also minus 3 times 2 plus minus 2 is going to give you minus 8. So this now gives us 1, 1, 1, 0, minus 2, minus 5, 2, 4, 1, and then we have 2, minus 8, 0, right? And then we do a similar thing, except this time we add minus 2 times row 1 to row 3, and this gives us 1, 0, 0, 1, minus 2, 2, 2, minus 8, minus 4, right? And now what we can do is we divide the second row by minus 2. So this is the same thing as just basically multiplying. I just want to make sure that this can be seen. Yep, so this is the same thing as just multiplying the second row by minus a half. So we do m2 minus a half. Because if you think about dividing by minus a half, it's the same as multiplying by minus 2. Or sorry, yeah, dividing by minus 2 is the same as multiplying by minus a half is really what I meant, but you see what I mean. And so from there, we can just continue, multiply by minus a half. This gives us 1, 0, 0, 1, 1, 2, 1, 5 over 2, minus 1, and then we have 2, 4, minus 4. And then what we can do is we can add -1 times the second row to the first row. So we're going to do a to 1 minus 1. And then this will give us the following system. So 1, 0, 0, 0, 1, 2. And I guess we get -3/2, 5/2, and -1. And then -2 for -4. And then what we can do is we can do a similar thing, or we just add -2 times row 2 to row 3. And so this gives us 1, 0, 0, 0, 1, 0, and then -3/2, 5/2, and -6. We have -2 for -12 here. And then what we can do to that, and I realize I've gone off the screen now, so yeah, let's just do it like that. I guess then what we can do is, let me see if I can get this on the screen. I'll probably move down to the next row here, because I've used up quite a lot of space. And then I guess then what we can do is we can now multiply the third row by -1/6, which gives us, so we just do that, and we just sort of m3 -1/6, which thus gives us the following. So it gives us 1, 0, 0, 0, 1, 0, -3/2, 5/2, 1, and then -2 for 2. Okay. And the last thing that we can do is we do so we multiply row 3 by -5/2, and then we add that to row 2. And doing that, it's a bit funky, but doing that you can get 1, 0, 0, 0, 1, 0, -3/2, 0, 1, and then -2, -1, 2. And the last thing you can do is you can add 3/2 times row 3. So a 3, 3, 1, 3/2 to row 1. And this gives you 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, -1, 2. Now, this is where we stop. And if it's not already clear why we stop at this point, well, we're swapping here because this system, we can now bring it back to, we can now interpret the system. So I guess the third step is interpret reduced augmented matrix. So there are a couple ways we can do this. Well, I mean, there's only really one way we can do this, but there are a couple different interpretations depending on what it looks like. But in this case, we can see that there's a 1 in this position here. So in our A11 is 1. So that basically corresponds to me having 1x. Our A12 is 0, so that corresponds to me having 0y. And the A13 is 0 as well, so that corresponds to me having 0z. And that's going to be equal to 1. So this is actually the same thing, this first row, as me saying that x is equal to 1. And similarly for the second row, this gives us that 0x plus 1y plus 0z is equal to -1, right? Y is equal to -1. And this seems familiar because it's what we got before, right? So we have 0x plus 0y plus 1z is equal to 2, and so we have that z is equal to 2. This is exactly what we had before, right? And so ultimately what we're trying to do in this case with our augmented matrix is get it down to this form here, where we have 1s in the diagonals and 0s elsewhere. There's a special type of matrix as well, which has 1s in the diagonals and 0s elsewhere, which is known as the identity matrix. But for now, just know that, understand that when we have linear systems, we want to get them into forms such as this, because it means that we can just basically read off our solutions, right? It clearly tells us that x is equal to 1, y is equal to -1, and z is equal to 2, right? Now, obviously, getting to that point is a little bit more arduous, but it's systematic, okay? And we only need to use those 3 elementary operations. Effectively, it can be proven later on that those three elementary operations are just enough to give us, to always find, to always reduce our augmented matrix to a point where we can just read off the solutions. So it's a lot more systematic, and we kind of know the point that we need to get to. Whereas with substitution, you don't really know where you're getting to in a lot of cases, especially in some trickier cases. You don't really know what you're doing. You're just trying stuff out and seeing if it works in many cases. And even in cases where there is sort of a systematic method, as we saw earlier, it still can, with lots of equations, be very, very long and tedious computationally as well. Obviously, like lots of operations happened here, the elementary operations, and so I guess technically, same would be true for a very large matrix, but yeah, it really just comes down to like how systematic it is in all cases, which row reduction is just sort of better in that sense. Okay, so how long are we at here? We're at 40 minutes. So next time I'm going to end there. Next time we can look at some more examples using row reduction, where there are going to be zero solutions and infinitely many solutions. And find out some stuff about linear systems, and then complete a system of equations involving a parameter alpha. Thank you guys for watching.